Math 265A, Cuesta College. I'm Joe Vasta, and we are going to cover 2.5 limits at infinity. So let's get started with this. This is actually different than what we did last time in 2.4, which was called infinite limits. So limits at infinity and infinite limits, will show you the difference between both of them. Let's get started. We have a picture of a graph of f. I did not label that, so there's f. And it looks like a rational graph. You know, it looks like it has asymptotes, vertical asymptote and a horizontal one. And let's go ahead and do some problems. We already know how to do some of these problems. And the first one is this. What is the limit of f as x approaches 1, so that's an x value, from the right? So here's 1. You are walking on the graph from the right. And what is the limit? What's the y value that you're approaching? Well, that happens to be negative infinity. And we talked about this in the last section. It's a kind of does not exist, but we call it negative infinity. It's an infinite limit. Now let's go ahead and do the next one. Problem 2. What is the limit of f as x approaches 1 from the left? So here's 1. Let's get on to the graph on the left part of that and walk along the graph approaching the x value of 1. And where's your y value going? Well, it's going to positive infinity, which is another kind of does not exist. And now what they're going to ask is, what is the limit of f as x approaches 1? Now this is from both sides, and because you've already done the right-hand limit and the left-hand limit and they were different, we're going to say does not exist. And think about it. Look at, here goes the bugs. They're walking along here. They're never going to meet at 1. So these guys here are called infinite limits. That was from the last section. And when you have an infinite limit at a value, an x value, like 1, then that gives you a vertical asymptote of x equals 1. Now, of course, you say, well, the graph already had 1, but this indicates that vertical asymptote. Now let's go ahead and do some new stuff. Here are limits at infinity. What is the limit of f? So this is going to be new now, as x approaches infinity. So now the little bug is taking a walk along the graph, and you're going off to infinity. So as you're going to infinity, what y value is that bug approaching? Well, there's a horizontal asymptote there, and this graph keeps getting closer and closer to it without touching. But the limit where he is going as he's walking toward infinity happens to be y value of 2. Now this is a weird kind of limit because this is one where we don't investigate the bug coming from both directions, because what's to the right of infinity? Well, infinity, you never get there. And so we are just saying, what is that bug getting closer and closer to in terms of y values? He's getting closer and closer to 2 as he goes off to infinity. So that's limits at infinity. Let's go ahead and find the limit of f as x approaches negative infinity. So now the bug is traveling on the graph toward the x value, well, toward negative infinity for x values, and he's getting closer and closer to the x-axis. And that has a y value of 0. So these two limits that we did are known as limits at infinity, which happens to be what this section is called. Limits at infinity indicate not vertical asymptotes, but they indicate horizontal asymptotes. And so horizontal asymptote, you're going to have values of 2 and 0. So I'll write those out. Y equals 2. Y equals 0. And we can see that up in this picture. Now, of course, we don't have the dashed line there, but it's going toward the x-axis. So the x-axis is a horizontal asymptote. Limits tell us, limits at infinity tell us the end behavior of your function. So in pre-calculus, you may have heard that word end behavior. It just means what is your function doing as it's going off to the right and as it's going off to the left. If a limit at infinity gives us a number, then that gives us a horizontal asymptote. And you may have remembered in pre-calculus, you learned some rules about horizontal asymptotes of rational functions. Those are polynomials over polynomials. Now we can find horizontal asymptotes of other creatures besides rational functions. Now I know some of you were like, wow, that was a lot that you said. So what I said is kind of summarized right here. And this will be included in the PDF. Now, what we want to do before we start doing more limits, I think we're pretty good with pictures. A lot of your homework is going to be doing the algebra of the limits. So I'm going to take these guys away here. Before we do limits with algebra, we have to do infinity arithmetic. And so infinity arithmetic is arithmetic using the infinity sign. So this is what I'm going to do. I'm going to put infinity plus 3. So what is infinity plus 3? Well, we're not going to say it equals, we're going to say that that goes to something. Well, if you just put 3 onto it, you are still going to infinity. Okay, so adding a number to infinity, like 3 or 7 or 5 or even a negative 11, it's still going to go to infinity. This is going to help us a lot. Now, a lot of calculus books will not write the infinity arithmetic. That's all right. We're doing things our way. So here's another one. You have infinity minus 3. Well, that tends to be what? The minus 3 is nothing compared to infinity. That tends to be infinity. Okay, let's try something with negative infinity. And think of the number line. You know, maybe you're thinking, oh, well, I can't grasp this infinity and negative infinity. So infinity is when you head off that way, and negative infinity is when you head off to the left. Okay, so what is negative infinity plus 3? Well, that's going to tend to, that plus 3 is not going to make much of a difference. Even if it's at plus 100, this is still going to tend toward negative infinity. And of course, negative infinity minus 3 is going to be negative infinity still. Let's continue. 3 times infinity tends to go to infinity. Okay, now it's going to get a little trickier. What do you think negative 3 times infinity is? Well, you have a positive infinity here. So a positive times a negative is going to be a negative, and this is going to tend to go to negative infinity. Let's do another tricky one. A positive 3 times a negative infinity. I don't know if it's that tricky. It's kind of like positive 3 times positive infinity, but positive 3 times negative infinity is going to tend to go to negative infinity. Maybe the trickiest one is this one right here. Negative 3 times negative infinity. Two negatives, you know, when multiplied together will give you a positive, and this is actually going to be, or go to positive infinity. I'll justify one of these pretty soon, but right now I'm just kind of giving you some arithmetic facts. The next few, well, we'll see. The next one you might think is kind of dumb, but I'll do it anyway. What's infinity over 3? What does that tend to? Well, it's kind of like multiplying infinity times 1/3. So it kind of reminds us of like some number, some fixed number times infinity, which is still going to go to infinity. The reason I put that is because I like to contrast it with this one. 3 divided by infinity. Well, this is saying 3 divided by a really large number. I mean, you could do that on your calculator, 3 divided by 1,000,000,000. That's going to tend to go where? That tends to go to 0. So, wow, we got something different besides infinity or negative infinity. So this is some infinity arithmetic. Let's continue. I think we need a little more here. Negative 3 divided by infinity. Well, that's going to be negative 3 divided by a really big number, like negative 3 divided by 1,000,000,000. It's going to be negative, tiny little number that's close to 0, and it's going to tend to go to 0. Okay. So if you have a 3 divided by negative infinity, once again, you still have a really large magnitude number on the bottom, and you have 3 over it. This is going to tend to go to 0. And the same thing with negative 3 over negative infinity. That's going to go to 0. Okay, the next one, this is a pretty famous one. This is infinity plus infinity. What is infinity plus infinity? Well, that actually tends to go to infinity. And you might say, well, how is that possible, Joe? Well, there's infinite amount of even numbers. So if you count the even numbers as it's infinity. And the odd numbers are infinity as well, and you add those together, you get infinity. Here's another one. It kind of blows your mind if you think about it too much, so please don't think about this too much. Minus infinity, or negative infinity minus an infinity, well, hopefully you can pretty much guess that that's tending to go to negative infinity. Here's another one. Infinity times infinity. Well, that's infinity. Negative infinity times a negative infinity tends to go to positive infinity because we have 2 negatives there. Negative infinity times positive infinity. Well, negative times a positive, this is going to be negative infinity. We can do like infinity times negative infinity, but I'm not going to put that on the list. So these arithmetic facts we're going to use, it's going to help us do these limits that we've been talking about, limits at infinity, and we'll see how this works out for us. I do want to mention, and we're not going to get them yet, but we will see them later on in calculus. These are called the bad boys. I don't think your book calls it that. So the bad boys would be like infinity divided by infinity. So some of you might go, oh, well, that's just going to be 1. But that's not necessarily the case. Then you have to analyze. It all depends what functions are on the top and bottom in terms of what this comes out to be. This is an indeterminate form. And there's a person who's going to help us with that later on, and his name is L'Hopital. Okay, there's another bad boy. Oh, another one would be like infinity divided by negative infinity. We don't, that's going to be a bad boy as well. But another one would be infinity minus infinity. So those are bad boys that include infinities. Another bad boy that does not include infinity would be 0 over 0. I'm not going to put them on this list because this is infinity arithmetic. And 0 divided by 0 is also something that can be dealt with using the help of L'Hopital. So I think we're ready to do some limits at infinity because we have our infinity arithmetic. So I think we're good to go. And this is kind of like what your homework will look like. So there's the first thing. Problem number 1. What is the limit of x squared as x goes to infinity? Well, let's think about what this is. This is going to give us infinity squared, which we said was infinity times infinity, and we've done infinity times infinity. This is going to go to infinity. Okay, let's do the next one. And then some of you are like, wow, calculus is really worthless. I'm not going to admit that right now. I mean, yeah, it is. I'm just kidding. Okay, so we're actually going to see applications of limits as we move on. Remember, we're trying to get to instantaneous velocity and derivatives and rate of change. But, you know, days like this, when you're looking at this, you're like, what am I doing? Okay, let's do the next one. This next one, we're going to go negative infinity squared, which is a negative infinity times a negative infinity, which gives you positive infinity. Now, there are going to be some teachers, and maybe I should have a problem with this, putting an equal sign there and using infinity like we are plugging in a value like a particular number. But for now, I just kind of want you to get this concept and not be stuck up with this, oh, we got to put an arrow here or whatever. We'll just do it this way for now. This last one, the limit of negative x cubed as x approaches infinity. So how are we going to do this? Well, this is really negative, and then we have infinity cubed. Okay, so what is infinity times infinity times infinity? It's infinity. And then we have a negative in front of that, so this gives us a negative infinity. Now, some of you might raise some objections to these examples here and say, well, Joe, we could have just thought about what the graphs look like, but when things are more complicated, this is going to be the way to go. Sure, I could have right from the beginning for problems 1 and 2. I could have drawn the graph of that parabola. And you can see, as x is going to infinity, where's y going? The limit is infinity. And as the bug walks this way to the left, his x values are going to infinity, the y values are going to infinity. So yeah, I do know we could have drawn the graph for this. And we could have also drawn the graph for this, which is x cubed that gets flipped on the x-axis. And yeah, we would have been able to verify that geometrically. But I think what we're working on right now is the algebra and getting ready for when it is more complicated. Let's go ahead and do a few more problems here. Number 4 is when it starts getting a little tricky. So on number 4, when you put infinity in there, you end up getting infinity minus infinity. And you're thinking, that's a bad boy. I thought we wouldn't get bad boys in our homework. What you got to do is do just a little algebra to this to turn it into something that we can analyze. So you can't always do that with bad boys. Sometimes with bad boys you need something called a derivative and L'Hopital's rule. But what I'm going to do, so think about this x squared minus x cubed. You're just looking at that. Where's this? So we can cover this up. Like, if you're just looking at that and then your teacher says, do something with that, and you're like, I don't know what to do. Do some algebra. I don't know what to do. So some people would go, let's stick 7 in for x. I don't know who would say that, but some people would do that because they'd panic. But you might think, hey, there's something I can do with this expression. I can factor out an x squared. So that's what I'm going to do. So this equals the limit as x approaches infinity, factor out an x squared, and then we'll see what happens to this problem. Okay, so I've just factored out an x squared, and when I put infinity in for x, what's infinity squared? It is infinity. So that's the first part, that's the x squared. And when I put infinity right here, I get 1 minus infinity. What is 1 minus infinity? It is negative infinity. And now I have infinity times negative infinity, which equals negative infinity. Oh, these are life skills that are going to get you far. Okay? If the plumbing breaks or you have to fix an electrical panel, this is so useful, as you can see. So, what do we have here? We actually have a theorem. So I'll put that theorem maybe in a different color. So this is a theorem. Looks like the same color. Okay, so let's try this again. Theorem. I'm trying to sit in a really bright room, so the paper will be bright enough. So I'm getting a lot of natural light. So sometimes after lectures I'm like walking into the wall because it's been bright all the time. Theorem. So I was trying to make an excuse why I picked up the black pen. Just because I'm stupid, I don't know. I just grabbed for a pen. The limit of a polynomial as x approaches infinity actually equals the limit of the leading term. Now, do we remember what a leading term of a polynomial is? It is the term that has the biggest exponent. So the leading term of this polynomial is negative x cubed. So instead of doing this factoring thing next time we have a polynomial, let's just do this. Does this theorem also have another part where it says x goes to negative infinity and x goes to negative infinity? Yeah, it does. In fact, we'll do that on this problem right here. Okay, so we have the limit as x approaches negative infinity. We have this polynomial. So by the theorem, even though we didn't write the other part with the negative infinities, we can write our limit. So the limit of this polynomial equals limit of the leading term. Oh, by the way, this only works when you have a negative infinity down there or a positive infinity. If x is approaching 4, you're like, yeah, let's just do the leading term, you're going to get the wrong answer. So it's only when you have a limit at infinity. Okay, so this is a little tricky, but we do want to be careful on this, okay? So look at this. This is negative 3. And I'll write this out here. So this is negative infinity. I know I didn't write out all the steps up here. Negative infinity to the 4th. So what is negative infinity to the 4th power? That is negative infinity times negative infinity times negative infinity times negative infinity. Good thing I didn't have a 17 there. So that's actually going to be infinity. What's negative 3 times infinity? That is negative infinity. And just a reminder, when we put negative infinity for our answer, it is a specific kind of does not exist. So we do want to put that symbol there. So that is problem number 5 on these limits and infinity. Let's go ahead and do some more problems. Problem number 6. Let's go ahead and put infinity in there. And so this is going to be 1 over infinity squared. Infinity squared is infinity. That's part of our arithmetic. And then here's some more arithmetic. And we saw this on our arithmetic page, except it had a 3 on it. So 1 over infinity happens to be 0. And at any time, you could consider the graph. In fact, I will on this one. But really, we should try to be doing this algebraically. The graph of this, if you remember from pre-calculus, goes like that. And that's not supposed to touch the x-axis. My hand slipped a little. And so as you're going to infinity, x is going to infinity, where's the bug going? He's getting closer and closer and closer to the y value of 0. So it all makes sense. Hopefully, it all gels up with the picture. Okay, our next problem that we're going to do is one that looks like this. So there's some negative exponents. I'm going to rewrite this expression here and write this as 1 over x to the 3rd. So that's what I'm going to do. So this is the limit. X is approaching negative infinity. And we have 6 plus 1 over x cubed minus 1 over x to the 4th. And we're going to negative infinity here. Okay, let's put negative infinity in. We have 6 plus 1 over negative infinity cubed is negative infinity. And then we have minus 1 over, the minus comes from there, and then negative infinity to the 4th power is infinity. In some ways, it doesn't really matter if that was a plus or a minus, because 1 over infinity or 1 over negative infinity, that tends to go to 0, and that one goes to 0 as well. And so my answer is 6. Okay, so that is what I end up getting. Now remember, the 6 would indicate that this function has a horizontal asymptote, y equals 6. If you care, and some of you are like, no, I stopped caring right when you boxed the answer, which is cool. Okay, let's go ahead and do some more problems. So, if you don't listen to a lecture on this, you just jump into your homework, you just look at your homework problems, they really do look intimidating. But if you just kind of stayed here during the video and worked out some of the problems or saw me work out the problems, then when you got to your homework you would think it's not as bad as it looks. It does look bad with all the infinities. Number 8. Maybe you can do this one on your own by pausing the video. Maybe do 8 and 9. Okay, so number 8 looks like this. I'm going to rewrite this, though, yeah, I'll do it. So I'm going to rewrite this expression. So limits, x approaches infinity, I'm going to write this as 1 over e to the x. Okay, so I'll do some of the arithmetic sort of in my head. What is e raised to the infinity power? Well, e raised to the infinity power is going to be infinity. So this is going to be 1 over infinity, and 1 over infinity, once again, the arithmetic, infinity arithmetic tells us 0. Now on this problem, it's the same function, but I'm putting a negative infinity in there. So yes, I can write it as 1 over e to the x, but I see that this is going to go right there, and the negatives are going to go away. So watch what this is going to be. This is going to be e I'll put that in. There's that negative, and then here's negative infinity. It's two negatives to make a positive. This is e to the infinity. Now, e to the infinity, like we saw over here, is just going to be infinity, but it's on the top. So this is infinity. Infinity is our answer. And you may have remembered this function from pre-calculus. This function is the exponential function. It's important. The more important one is e to the x, but e to the negative x looks like this. Whoa. Like, kind of comes through here and goes like this. It's pretty weird. It's the airplane comes out of the sky and approaches the runway. And then this is the freaky part. This is the Twilight Zone. It will never land, but it will keep getting closer and closer. That's crazy. And anyway, oh, why am I doing this? Because as you go to infinity, where's the y value going? It's getting closer and closer to 0. And as this graph goes to negative infinity, the y value is going to infinity. So this tells us about the graph. Let's continue to do a few more of these. I bet you can do these ones on your own. Pause the video if you need. Here it goes. I'm going to go ahead and put infinity in there. 2 to the infinity minus 1. 2 to the infinity is what? Well, that's infinity minus 1, which is infinity. Limit of that function as x approaches negative infinity. Let's go ahead and put negative infinity in there. So I have a negative exponent. I'm going to cross the line, change the sign. 1 over 2 to the infinity minus 1. 2 to the infinity is infinity minus 1. And what's 1 over infinity? 1 over infinity is 0. So I get a final answer on this one of negative 1. Now you might remember back to your pre-calculus days when you had the exponential function. This is actually an airplane taking off that shifted down 1, and you had a horizontal asymptote of y equals negative 1. And you can actually see this helps us figure out some of those graphs. Okay, so that is problem number 11. Let's see if we can find 12 here. Problem number 12. Now that looks a little tougher. And so how are we going to do this problem? We are, well, you could put the infinity in and you really end up getting like the leading term on the top is it's going to give you infinity over infinity, and so that looks like it's one of those bad boys. And it is initially. Okay? Because the leading term on the top is going to dominate and the leading term on the bottom is going to dominate the bottom. So you will have infinity over infinity. But here's the trick to any of these problems. And I'll write it out here in red. You want to divide by the highest power in the denominator. If you forgot denominator, that's the bottom. So the highest power in the denominator happens to be this guy right here. So I'm going to circle this because that's what we're looking at there. So what I'm going to do, so I mean this does tend to go infinity over infinity. I'm going to go like this. So this equals the limit as x approaches infinity. And this right here is a fraction. So I can multiply top and bottom by 7. I really don't want to do that. I'm going to multiply top and bottom by 1 over x squared. And then on the bottom, 1 over x squared. And so that's what we mean by divide by the highest power in the denominator. The highest power in the denominator is the squared, so we're going to go 1 over x squared. Maybe that could be written a little nicer, but oh well, it's written. So I have, let's just write this out, 8x squared over x squared. I'm sure some of you can skip this step. Plus 2x over x squared minus 3 over x squared. This is all over 4x squared all over x squared minus 5x all over x squared plus 1 over x squared. So this little rule will get us the answer in a lot of these problems. Because watch what happens. This is the limit as x approaches infinity. This guy right here is just an 8. 8 plus 2 over x minus 3 over x squared. That's what's on the top. Looks like we've ruined this rational function here, and now we've made it look really ugly. But beauty's in the eye of the beholder, so watch out using those words. So 5 over x plus 1 over x squared. Now, as x approaches infinity, this is 2 over infinity. That's going to go to 0. 3 over infinity squared, or 3 over infinity, that's going to tend to go to 0. So all these guys, like 5 over infinity is 0. 1 over infinity squared, or 1 over infinity, is 0. And the only people not going anywhere because they don't have x's is this 8 and this 4. Well, that's what this is going to be. 8 over 4. Please don't leave your answer like that. The answer for this limit is 2. So when you do your test, you do want to show your work on these. Divide by the highest power in the denominator. Now I do want to let you know that when you took pre-calculus, you did learn rules for polynomial over a polynomial. And remember that one of the rules happened to be if the degree on the top is the same as the degree on the bottom, then put the leading coefficient of the top over the leading coefficient on the bottom, and that's pretty much the rule. I mean, the rule in pre-calculus, your teacher may have said you just do that, just remember the rule. But now in calculus we can see why that gives us the horizontal asymptote, because we're going to infinity and it works out that way. Let's go ahead and do another problem that looks similar. It's going to be another rational function. So there it is. Problem number 13. Maybe you want to do problem 13 on your own. If you're having, pause the video. If you're having a hard time getting going, you are going to divide by the highest power in the denominator. What is the highest power in the denominator? It is the 3. So I'm going to multiply. I'll say multiply 1 over x cubed and 1 over x cubed. So this is going to equal the limit as x approaches negative infinity. I'm going to speed up this problem a little, and I'm going to write this as x squared over x cubed, which is really 1 over x. And the next one's going to be minus 3 over x squared. Meanwhile, on the bottom, we have a 1 plus 5 over x minus 1 over x cubed. It's correct. If you put negative infinity in this, you're going to get an infinity on the top and a negative infinity on the bottom. Infinity over negative infinity is a bad thing to have. But by dividing by the highest power in the denominator, you end up getting something that you can now do. When I put negative infinity in for this first x, 1 over negative infinity, 0. 3 over negative infinity squared, which is 3 over infinity, 0. This 1 I'm not going to touch. 5 over negative infinity, 0. And then 1 over negative infinity cubed, 0. So you might think, well, look, Joe, it's undefined. But watch this. On the top, you have 0, and on the bottom, you have 1. That is not undefined. This is really saying what number times 1 gives me 0. So you can do this. That number would be 0. It's when the 0 is on the bottom that we have a problem with. So the answer to this limit is 0. Let's go ahead and do another one. This guy right here, number 14. Maybe you can pause the video and see if you can do this on your own. Okay, I'm going to look at the highest power on the bottom, which is a2, and I'm going to multiply top and bottom by 1 over x squared. So this is going to give me limit as x approaches infinity, and this is going to look a little different now. It's going to be x minus 2 over x plus 3 over x squared. Now on the bottom you're going to get 5 over x squared minus 2. Okay, when you go ahead and put infinity in, 2 over infinity, 0. 3 over infinity squared, or 3 over infinity, is 0, or goes to 0. 5 over infinity squared goes to 0. Look what happens now. This one is just an x, so when you put infinity in for that, you have infinity, and on the bottom you have negative 2. What is infinity divided by negative 2, or negative 1/2 times infinity? It's going to be negative infinity. So if you were graphing this as your graph was going off to the right, it would be going down, if you cared about graphs. Okay, let's continue. This one, I would recommend that we just do this one together, okay? Because this one has some trig in it, and it's kind of a weird problem. So what I'm going to do is, this tends to go to infinities on the bottom, and on the top it's like oscillating between negative 1 and 1. So what do we make of that? Let's go ahead and squeeze. So this should sound familiar. The cosine in between what two values? It's squeezed in between negative 1 and 1. And that's because here's the cosine graph. Y equals the cosine of x. It's just oscillating between the two heights of 1 for the high and negative 1 for the low. Okay, so now what I'm going to do is, I really don't want to find the limit of the cosine. I want to find the limit of the cosine over x. So I'm going to divide everything by x. So really, when I do that, I'm going to assume, and it's not really an assumption, a big assumption, because I'm going to infinity, x is positive. Now why is that important? Because if I multiply all three parts by a negative number, those inequalities are going to flip. But I'm concerned with positive x values because that's where I'm going. So I'm going to multiply or divide by a positive number. Okay, now I'm going to go ahead and zap each part with a limit. Limit as x goes to infinity of negative 1 over x is less than or equal to, here's the meat of the sandwich here, limit as x approaches infinity of cosine x over x. Oh, by the way, that's our original problem. and then is less than or equal to, where am I getting this? I'm just putting a limit in front of this, a limit in front of that, and a limit in front of that. And so this is the squeeze theorem. You're squeezing that yellow thing in between the other two. So this is the limit as x approaches infinity of 1 over x. Well, we know that this one right here is negative 1 over infinity, so this one is 0. I'll just say this one goes to 0. And this one right here also goes to 0 or equals 0. And so, by the squeeze theorem, this guy goes to 0 as well, so 0 is the answer. And the squeeze theorem is it's one of those things that people don't like to see, because they're like, oh no, I'm not going to remember all of this. Well, do your homework, and if you have any questions, remember just to email the questions to me. But there is the limit, it is 0. Let's go ahead and do another problem. Problem number 16. This one's not as bad. Okay, probably the worst one was number 15. So problem number 16 is the limit of cosine x as x approaches negative infinity. Now this one might be the best one to just draw the graph. So what's happening as, I'll go like that, as this graph, oh, that looks pretty ugly, as the x values are going to negative infinity, well, where's this going? It's like, I don't know where I'm going, I don't know where I'm going, I don't know where I'm going, I'm oscillating between negative 1 and 1, and it's always going to do that. So what do you think that limit's going to be? It's going to be, does not exist. And that's what it is. Okay, so let's sum some things up here. And I pretty much gave you this information, but I'll put this in the note sheet as well. It's this right here. Asymptotes and limits. If any of the three limits, limit as x approaches a, or a from the right, a from the left of the function, give infinity or negative infinity, then x equals a is a vertical asymptote. And that was our infinite limit that we did in the last section. And we also did it at the beginning of this section. Now, if any of the two limits, and these are the limits at infinity, give a number a, then y equals a is a horizontal asymptote. Okay, before we do our next problem, let's review some algebra that usually people forget, or sometimes teachers don't cover this. So for this problem right here, I'd like to know what the square root of x squared is. And a lot of people would say, well, Joe, that thing is just x. Well, that does work if you have like a 5. You plug 5 in for x, you have a 5 on the right-hand side, and you have a 5 squared, which is 25. Square root of 25 is 5. 5 equals 5. But if the x, so this works for x positive. So this is true. I guess we can box it. If x is positive. But, okay, well, before I write the next thing down, if you put a negative 5 in for x, x is negative 5, you have a negative 5 here, and then negative 5 quantity squared is 25, square root of 25 is 5, so you get 5 equals negative 5. So this actually equals negative x if x is negative. So think about this, like if x is negative 5, then on the right hand side you have a minus negative 5, which is a positive 5, and then you put negative 5 in there, you get negative 5 squared, which is quantity squared, which is 25. Square root of 25 is 5. So you may have had something like this in an algebra class, and they would say, well, if you want to cover all bases, you would say the square root of x squared equals the absolute value of x. Now, I don't want to freak us out too much, so I'm not going to write that. But I'm going to give you another similar problem. Like if you had the square root of x to the 6th. Well, you square roots take out pairs. So you look, there was a pair of x's, so then you just had like an x there. So there are 3 pairs of x's, and you're going to end up getting x to the 3rd. You could also write the square root as the 1/2 power, and then 6, x to the 6th raised to the 1/2 would be x to the 3rd. Well, this is only going to happen if x is positive. Otherwise, if x is negative, then this thing is going to be negative x cubed. So this is if x is negative. And if you don't believe me, you know, like put x equals -2 in. So we'll cover up that negative. -2 times -2 times -2 is -8, and then you have a negative in front of that, that's +8. Over here, you have -2 to the 6th power is going to be a 64. Square root of 64 is +8. So this tells you the truth here. So what we're going to do is we're going to take a look at this problem that tells us or asks us to find the horizontal asymptotes of something that is not a rational function. You might think it's a rational function because you have a fraction, but a rational function technically is a polynomial over a polynomial, and the top is not a polynomial because of that radical. Okay, so how are we going to find the horizontal asymptote? Or there could be more than one. We're going to hit this function with limits at infinity. So we'll hit it with x going to infinity, and then we'll hit it with x going to -infinity. And so let's see here. I know my camera is about to turn off. Some reason it turns off after about 50-some minutes. One time it didn't, and that's what happens, you know, when you get your camera at a garage sale. Let's take the limit of f as x approaches infinity. So what is this? What am I going to do? I'm still going to do the same rule where I divide by the largest power on the bottom, or the largest term, the term that has the largest power on the bottom. So that's what I'm going to do. I'm going to go ahead, see what color I was using when I did that. Was it green? It was green. So I'm going to multiply the top by 1 over x cubed. I'm going to multiply the bottom by 1 over x cubed. And we're going to see what we get. I kind of wrote it right there. That's all right. So look what I get. On the top, I end up getting square root 9x to the 6th minus x. This is all over x cubed. On the bottom, I get x cubed plus 1 over x cubed. So what I want to do is turn this into something that has a radical. And so I know that's a tricky thing, but look at, see this radical here? It is 9x to the 6th minus x. I want to turn this one in so it says square root. It's not going to be x cubed, it's actually going to be x to the 6th. You can look at that last piece of paper and it says the square root of x to the 6th is x cubed. If x is positive, and guess what? X is positive because it's going to positive infinity. On the bottom, I'm going to go x cubed plus 1 all over x cubed. I know I didn't put my limit. Doesn't look like I have room to fix it, but I do. Watch this. Some white out. Put an equal sign. Here's the limit as x approaches infinity. Okay, so this is going to be the limit as x approaches infinity. you can kind of make that into one big square root. So this is the square root of 9x to the 6th minus x all over x to the 6th. This is all over x cubed plus 1 over x cubed. This is the limit as x approaches infinity. So we can do what we've been doing in those other problems. This is really just going to say 9 minus 1 over x to the 5th. So 9 minus 1 over x to the 5th. And down here, this is going to say 1 plus 1 over x cubed. You're putting infinity in for x, so 5 over infinity to the 5th, that's 0. 1 over infinity is 0. And so it looks like what you're going to get is the square root of 9 over 1, which is 3. So when they ask you to find the horizontal asymptotes, well, this could be it. Let's put it up here. So one of them is y equals 3. Okay, need another piece of paper. In fact, I'm just going to go ahead and cover up part of my work because I still want to see my function. Now I want to consider the limit as x approaches negative infinity. Okay, as x approaches negative infinity, I want to do the same thing that I did in green. And so when I do the same thing I did in green, I'm going to have this right here. Oh, I didn't write the limit right here. Well, now I did. Some of you must have been laughing when I was like, I caught myself, and it wasn't written there. So this is the limit as x approaches negative infinity of this thing, because I'm doing the same thing. But here is the subtle difference now. Okay, so this is the limit as x approaches negative infinity. Probably didn't give myself enough room there. This x cubed, you know, last time we wrote, oh, well, that's just going to become the square root of x to the 6th. Well, it can't be. Remember, x is a negative number, and if x is a negative number, then the square root of x to the 6th equals negative x cubed, or vice versa. You can say negative this root x to the 6 is x cubed, and that's what we're going to say. So this x cubed gets replaced with that right there. And why the negative? Because of this right here. I'm going to speed things up a little. So you can do one square root on the top. And look what we have. We have the limit as x approaches negative infinity. We have the square root of, you can do the same thing we did before, 9 minus 1 over x to the 5th is under that square root on the top. But look, there's a negative down there, so bring that negative right up there. This is all over 1 plus 1 over x cubed. Now as you're going to negative infinity, 1 over negative infinity to the 5th is 1 over negative infinity. That's just going to go to 0. And so will this. And you're left with negative root 9 over 1, which is negative 3. So as you're going off to the left and following the graph, it is getting closer and closer to negative 3. When you went to the right, it went to 3. So this actually has two horizontal asymptotes. Y equals 3, y equals negative 3. And so there's the answer. This will be a lot less stressful than the squeeze theorem and the last problem that we did. So let's go ahead and work out this problem here. I'll put some tick marks. 1, 2, 3, -1, -2, -3, 1, 2. Maybe I should have done this before I had it all written out except that. Okay, so let's see what we have here. It says f of -1, I'll do the graph in blue, is -2. So -1, -2, I'm going to put a dot right there. So the function has to go through that. F of 1 is 2, so I'm going to put the point 1, 2, put a dot right there. F of 0 is 0, so I'm going to put a blue dot right there. Now, these limits at infinity have numbers, which means you're going to have a horizontal asymptote at y equals 1 and another one at y equals -1. So I might as well put those horizontal asymptotes. Should I be a perfectionist? Maybe I should. Use a ruler. It's not looking that good. Looks a little sloppy. Oh well. So I have another one here. So there are 2 horizontal asymptotes. So what I have to do is make the graph go through those 3 points. I think I can do that. How could I do that? I can make it curvy or I can make it a straight line. I'll make it curvy. So I'll just go like this. Now some of you are going, wait a minute, your graph went through the horizontal asymptotes. Those horizontal asymptotes only are guides for what's happening as your graph is going off to the infinities. So this says as you're going to infinity, the limit is 1, so this one had better get close to that. Now could I make it go through that horizontal asymptote another time? Yeah. I don't know. This doesn't look like it's the maximum, but who cares? And then the limit as x approaches -infinity, so as you're going to the left, you're going to end up getting close to -1 for your altitude, for your y value. So we'll go like that. There are many possible answers. That's why they say sketch a possible graph. We better identify vertical and horizontal asymptotes. Well, I don't see any vertical ones. But maybe problem 87 has one, and I'm going to say, well, this one is y equals 1, and down here is y equals -1. And so that is how you do problem number 86 in your book. Continue to keep on top of the homework. Keep doing the homework. We are done with 2.5. Our next section is 2.6. Have a good day.